everyone, hope you all safe with the good health. With you, Ms. Dina Badri, science teacher for grade 8. Today, we will talk about properties of the wave. Lesson 2 in Unit 1. We talked last time how can we describe a wave. We talked about the amplitude. We said that it is a measure of how far the particle in the medium move away from their normal rest position. And we talked about the wave. We said that the wave is a distribution that transfers energy from one place to another. And what is the meaning of the wavelength is the distance from any point on a wave to an identical point on the next wave. So when we talk about the wavelength, it is the distance between two crusts, not between crust and trough. Okay? So did you see this wave? What is the wavelength of this wave? What is the wave amplitude? This is the wavelength, crust and crust. But this is amplitude. Okay? Another property is the wave period, the time required for one wave to pass a given point. Okay? So, a wave period is the time required for one wave to pass a given point. There is another way to express the time of the wave cycle is a frequency. What is the meaning of the frequency? Frequency of the wave tells how many cycles occur in amount of time. Okay, so frequency is the number of the wave in 1 second. Frequency is measured in hertz. So when we talk about the speed, it's measured in unit meter per second. Wavelength by meter or centimeter or kilometer, okay? But the frequency is measured in unit with a hertz. 1 hertz is equal 1 wavelength per second. Frequency is the inverse of period. What affects the energy of the wave? Some waves carry more energy than others. For a mechanical wave, amplitude is related to the amount of energy the wave carries. For two similar waves, the wave with greater amplitude carry more energy. Greater frequency can also mean greater energy in a given amount of time. So, electromagnetic wave, EM wave, EM is simplification for electromagnetic wave. Energy is most stronger related to frequency. Okay, so the electromagnetic wave more stronger than any other wave. As a wave moves through a medium, particles may move in a different direction or come to rest in different places. Okay, so when a wave starts to move through a medium, particles may move in a different direction or come to rest in a different places. As the wave travels through more of the medium, more energy is lost to the medium. When a wave has high frequency, it means it loses energy more than lower frequency wave. Okay, for example, when you stand far from a concert, you might hear only the low frequency passive sound. Okay, many waves spread out in circles or spheres called wave fronts. As the circle expands, there is less energy available on the wave fronts. So, what determines the speed of the wave? Wave speed or the speed of the wave depend on the properties of the medium. Wave tends to travel more slowly in a denser medium. Okay? In gases, wave speed is higher at higher temperature. All electromagnetic waves travel at the same speed in empty spaces, but they travel more slowly through denser medium. Wave speed can be calculated from the frequency and the wavelength. Speed is the distance divided by time. It is the speed, but the wave speed of the equal its wavelength divided its period. The relation can be combined with the relation between the wavelength and frequency. Wavelength is equal to the wave speed divided by the frequency.
Waves. One of the first things we need to know about waves is there are two different types of wave. One, shown here by waves in the sea, and the other one shown by sound waves. So how are they different? Well, first let's look at the sea waves. If we look at them represented with this slinky, we see that the vibrations are at 90 degrees or perpendicular to the direction of travel of the wave. These are called transverse waves, and examples of them are waves in water, waves on a string, or light waves. Now let's look at the sound waves again. Again, we see them represented by the slinky, but this time the direction of vibration is parallel to the direction of travel. These are called longitudinal waves, and the only example you really need to remember is sound. One really important thing to remember about waves is they only transfer energy from place to place, not any matter. And we can see that here by looking at a lovely rubber duck sat in a bath. As a wave goes through, the duck bobs up and down, but once the wave's gone, he's back to his original position. The wave has carried energy through, but it did not carry the duck with it. Finally, we need to know some key features of waves. First off, wavelength. A wavelength is the length of a full cycle of a wave, from one point to the next same point. It's easiest to think of as the distance from crest to crest or from trough to trough. And we measure it in meters, and it's given the symbol lambda, a nice Greek symbol. The amplitude is like the size of a wave, but we need to remember that it's measured from the equilibrium position, or the central line, to the crest, not from the crest to the trough. Finally, frequency, which is the number of complete waves to pass a point every second, and it's given the unit of hertz. So an example of this would be if 10 waves pass in 2 seconds, the frequency would be 5 hertz. Using these things, we can actually now calculate the speed of a wave using the equation speed equals frequency times wavelength, or to give it in symbol form, V equals F lambda. So there's a lot to learn here, but once you've learnt these core concepts, it will give you much more confidence in the rest of the topic.